Line A1, learning task 5, we're going to go and take a look at solving some vector problems. So we took a look at vector components in our previous learning task number 4, where we defined that a vector is something that is going to go and have magnitude and it's going to go and have direction. And we took a look at how we could go and plot a vector inside of a quadrant system by knowing what our x's and our y's themselves were going to go and be. Now what we're going to do is we're going to start to go and take more than one vector and we're going to start placing them together. And really this is a common thing that is done. It's just done unconsciously by us most of the time. We take things like we series together voltages, which are going to be forms of force that have direction, positive or negative, force being the magnitude of voltage, and therefore we're going to get a vector result out. We do resistances, impedances. We don't know we're necessarily adding vectors as we're doing them in the field, but we're going to go through that and explain what those vectors themselves actually are. Let's start with some easy cheesy vectors over here. We've seen this before. This is where we're seriesing together a couple of batteries. I apologize for the really granular look. It's just the way that my digital copy came through, but you should recognize that as being the same as what you have inside of your book over there. It shows that we can have a schematic diagram showing that we have got two voltages placed in series. Now, you're all second year. At this point, you know that if you take a 12-volt battery and you take another 12-volt battery and you series them together, that you should go and have across the top of that thing 24 volts, and that the positive should be over here and the negative should be over here. This is just what happens when we series batteries together. However, what we can do is we can take these forces, these voltages, and we can describe them as being a set of vectors. Over here, we're going to go and describe A as being 12 volts, and we're going to go and place it on the 0 axis. Because there was no angle given to it, we are going to go and put it at a value of 0. Anytime we got DC, DC is just going to be a 0 value for us. We take a look at our second battery, it's also 12 volts, and we are going to go and place that in there. And what we know is happening is we first finish up one vector. So here's our point of origin. We draw one vector, and then we go and have what's called the tail over here, and we've got the tip of the vector over here. We're going to go and add the next one, tip to tail. So the tail of this one starts out now as the new origin, and we continue on from there. So we see that the one vector adds to the other vector. We together have this in series aiding, and we could form a total equivalent vector across the bottom of this thing, which would be our 24 volts, or what we refer to as the resultant. This is going to go and be a graphical method, meaning that it's done through the use of pictures and measuring and things like that. Now, it's really handy when we've got two that are going to be in the exact same direction. You know, it's really easy to see how we can add them together. Where it starts to get a little bit tricky is if we did not have them in the exact same direction. At that point, we'd have to start using a protractor or something like that. That sounds like a lot of nonsense. I don't even know where my protractor is, much less if I even have a protractor anymore. But if I did, I wouldn't want to bother with trying to go and draw out lines and copy them through. It's much easier to learn the mathematics that are going to be behind it. Before we go into adding something that is going to be a little bit out of phase, let's continue adding in some stuff that is going to be in phase over here, but now we're going to put it in series opposition instead of in series aiding. That would be this over here. You should also be familiar with this, that if we take a 12-volt battery and we take another 12-volt battery and we connect them negative to negative or positive to positive, it wouldn't matter which one, but if we connect them so that the same polarity is going to be over here, we're going to go and get cancellation of the total amount of voltage that we would go and have out of them. Particularly, we're going to go and get cancellation of the amount of volts that we are going to go and see. We see that one's going to be 12 volts, one's going to be 6 volts. And what I can do is I can add them together as vectors. Once again, I'm going to start on my A1 over here. We could start on the B, it wouldn't make any difference. But I'm going to start on one, and I'm going to go and draw out its voltage as a vector. So here's my point of origin. I'm going to draw out that voltage on there. Then what I'm going to do is I'm going to add tip to tail once again. Now they show it a little bit above, just so that it's clarified, but really what they're doing is they're starting the second vector, and they're running the same vector back. And what we see is that we get that cancellation, leaving us with a net amount of 6 volts that we are going to go and have here. This would be what we refer to as a series opposing type of circuit. We see that the resultant vector that we are going to go and have, the 6 volts, is in the same direction as our original large one because we've only canceled out 6 volts out of our original 12-volt battery by seriesing in this 6 volt over here. If we were to go and reverse this 6-volt cell that we have here, we should also be able to do the exact same thing now. And let me just start that one out here with a origin here. add in our 12, we could add in a 6, and we should be able to see that then we would get the equivalent of 18 if we were to go and change these ones around. Make that positive, make that negative, put them into series aiding, we would see that we would get up to that 18, whereas when we stick them in series opposing, we knock the whole thing all the way back down to this 6 volts. It's a really, really simple vector addition. What are my angles that these vectors are at? Before we proceed any further, the book doesn't ask about that, but I think it's really important to go and ask about these angles because it's going to help us later on with our calculations inside of here. Let me just go and erase a bunch of this stuff. We're back on figure number 1. What are my angles that I'm at? Well, remember that with my quadrants, this is angle 0, and then we go all the way up and around, right? So if this is where my origin is, this is lying right along that 0 axis, so really I could go and write this thing out as being, and I'm going to do that over here, 12 at angle 0 plus another 12 at angle 0. We're going to come back to that later on. We have to come back to that one later on because we've got another methodology that allows us to solve it using this thing at an angle. Looking at these, what would I do for my angles off of this? Well, once again, starting over here, I'm going to go and see that this is going to be at angle 0, but this one is facing back in the opposite direction. So if it's facing out from the origin, if I were to draw it as a standalone vector, we would see that this thing would be at 180 degrees. We'll place these in here. We'll say 12 at angle 0 plus 6 at angle 180. Once again, we're going to come back to this one a little bit later on once we get a bit further through these. That was where we had them directly aiding or directly opposing. We saw that we would just add them together or cancel them. As soon as we get them 90 degrees out of phase, we're going to have to go and add them once again tip to tail and find a resultant out of these things. We are going to have a lot of 90 degree out of phase vectors this year. Everything that we deal with in inductance and capacitance is going to deal with the fact that it is 90 degrees out of phase, leading or lagging. So we have to be able to do this calculation really, really effectively. Taking a look at the first one over here, we see that they're showing us we've got two separate vectors. We've got 60 volts that's going up at 90 degrees. We've got 80 volts that is going out at 0 degrees over there. So what I'm going to do is I'm going to add these two vectors together to find the result. So adding vectors finds you the result. We're going to take 80, and then I'm going to go add tip to tail over here, add my 60 volts onto there. And when I go and do that, I can then draw across. If I drew this all to scale, I could draw across from there to there, and I could go and measure that using the same scale, and I would find out that I would be at a value of 100 volts that I'm going to have over here. Instead of measuring, I could also go and just use Pythagoras, right? We've got B side, we've got an A side, we can go and find our C side over here. So A squared plus B squared, and take the square root of that, will get me out to my C off of this one as well. Either one of those methodologies is going to go and work. You could even take it one further if you want it. You could even take these two together and use tangent. Use tangent to create the angle once you've created that angle, and then go and use one of these A's or B's to go with that angle and create your hypotenuse that you would go and have. Any of these methods work. It's all just math. You know, you pick the one that's going to go and work for you there. Okay. That covers our easy ones, the ones that are going to be either series aiding, 0 degrees difference, or the ones that are going to be series opposing, 180 degrees difference, or the ones that are going to go and be 90 degrees out. We can use Pythagoras. But as soon as we go to ones that are no longer a full 90 degrees out, things start getting a little bit more tricky. Let's take a look at this set that we have over here. First of all, if we were to do the graphical method would involve us taking the first one, number 1. I'm going to draw these in order. Number 1, it would be a value of 8 at an angle like that. Then I would go to a value of 6 at an angle like that. That's going to be number 2, right? It's going up at 90 degrees over there. And then number 3, which is a value of 10 going down like that. So I know that, just kind of roughly sketching this out, that I should end up at something down here that's going to be a slightly negative angle. However, how big or how small is really difficult to do. And even if you do this with a scaled set of calculations and a protractor, it's still going to involve a lot of extra work. Instead of doing that, what we're going to do is we're going to go and break these down into values, into what we're going to go and refer to as our rectangular values, and then those rectangular values we are then going to go and convert into X and Y columns and add them together. Here's what we mean with that. Let's just start by taking a look at number 1. I'm going to make 2 columns over here, X and Y, and then I'm going to go and start with my number 1. What is my magnitude of X displacement? Well, let's see, my magnitude of X displacement is going to be 8. And my magnitude of Y displacement is going to be 0. It doesn't come off that axis over there. If I take a look at this one, number 2, I see that my magnitude of Y displacement is 6, but I see that my magnitude of X displacement is going to be 0 because we don't move off of that same axis over there. Now we come down to this one. This one over here, we've got a 60 degree and we've got a value of 10 that we are going to go and have. 300 degrees is what it's actually at, but we could also call this thing a negative 60, and we need to have that so we can form a small triangle that's going to be inside of here. Let's go and use our SOHCAHTOA to go and solve what we have. We have our hypotenuse. I'm just going to draw this thing over here as a triangle. Triangles can be right side up, they can be upside down, it doesn't matter as long as I know what angle I'm looking at. That's that one over there, 60 degrees. And my hypotenuse in this case, that is going to be a value of 10. So I can go and find my adjacent, which is going to be, in this case, my X value, or I can go and find my opposite, which is going to go and be my Y value. Let's go and find our cosine. So we know that the cosine of 60 is going to be equal to my adjacent side, that's going to be my X value, over top of my hypotenuse. My hypotenuse has got a value of 10, so I can go and take 10 into the bottom over there, and then I'm just going to cross multiply that up to this side over here. And that tells me that if I go 10 times cos 60, I should end up at my value of X. Let's just do that. 10 times cos 60, which gives me an X value for this thing that is going to go and be 5. So if I take a look at it, I see that it's got a value of 5 going out along here. It's a positive 5 that I'm going to go and have. Let's go and do our Y values. Our Y values are going to be based off of our sine. So sine of 60 of this angle is equal to my opposite, which we don't have, but it's a Y value, and we know it's a negative Y value, but we'll get to that in a minute. Y over top of my hypotenuse, which we do have a value for, that's going to be 10. So it's going to be the same look to our formula. Once again, we can isolate for that Y by multiplying that 10 over to this side over here. And when we do so, we'll move that one over there. Now we can do 10 times sine 60. So 10 times sine 60, which gets me to a value of 8.66. What we'll note about that 8.66 is that that 8.66 would have to be a negative 8.66 because we're going down off of the origin, and this is going to be a negative Y value. So this is going to become negative 8.66 that we are going to go and have over here. Perfect. So now that we've got all of that done, oh man, there's a lot of work involved with these. We see that this is going to be 13. We're just going to add all the x's together. So we've got a total x displacement of 13. That makes sense. We see we're kind of continuously moving over towards the right to the positive x. But we see that my y displacement goes up 6, but then comes back down negative 8.66. So we're going to cancel 6 out of this basically, leaving us with only negative 2.66. As soon as we've got this x and this y value together, we can place them into a triangle. You should have a triangle that's going to go and look something like that. What you could do now is you could go and solve from this using Pythagoras, your x squared plus your y squared, and then take the square root of all of that. As soon as you put that all into Pythagoras and punch that in, 13 squared plus negative 2.66 squared, take the square root of that, it's going to bring you to a value of 13.3 amps that we are going to go and have. So this vector that we sketched out before has got a total magnitude of 13.3, where it's going to go and end up at. What angle is it ending up at? Well, from this we would have to go and use some sort of a trig function to go and get to that. Now we could go and use cosine or sine, however, they would be poor choices because what we would be doing with cosine or sine is we'd have to go and use the hypotenuse. And we've already developed that hypotenuse off of these values, which we've already done a little bit of rounding and stuff like that inside. So we're just going to go and compound our error. Let's work with the most accurate numbers that we have, which would be my tangent for this. I know that the tangent of theta is going to be equal to my opposite, negative 2.266, over top of my hypotenuse, hypotenuse adjacent, which is going to be a value of 13 over here. That would get me to tan theta. If I want to move this tan and just leave the angle on itself, I'm going to have to go and get rid of the tan over here, and I'm going to have to go and insert it as a inverse tan on the other side. I should have left myself a little bit more room, but well. Tan negative 1, like that. And when we punch all of that into our calculators, it's going to go and spit out a negative angle off of that. Let's just go and do that. So we're going to go with, clear that there, inverse tan of bracket negative 2.66, that's too many sixes there, divided by, and then we're going to take our y value over there, our x value over there, the 13. 2.66 divided by 13 bracket equals negative 11.56. In your book over there, they do have a little bit of a rounding error off of it, or not a rounding error, but they've just done some rounding and they end up at 11.6 instead of 11.56 off of it. So really, when we take a look at it, it's about almost about a negative 12-ish that we're going to be off there. Does that line up with what we have over here when we rough sketch it? Absolutely, it does line up with that. Negative 11.6, we'll call this. We could write this as being either angle negative 11.6, or we could go and write this thing by taking it out of 360 degrees, taking it all the way around back to the other side, which would then be, hold on a second, 348.4 that we would have on the other side, like that. It's a lot of steps to go through. They teach you how to do it inside of this one over here. Let's go and take a look at the next one. The next one over here does the same thing, except now instead of us having two of them that are going to be already on an angle, these ones here, we had 8 and 0, 0 and 6. Now they start to give us a whole pile of different ones that need to be broken apart. So this one over here would need to be broken apart, as well as this one over here would need to be broken apart. And so what we would end up having is something that would represent this. So if I were to go on x, y this, I'm just going to do the short form like this. Actually, why don't I use a gray so that we can line up our colors. X and a y like that. If I were to go on x, y this, I would see that I'm going to go and have some sort of a number for this, and then a value of 0 for my y. So for the green arrow, I'm going to go and have number. We're just going to call that a number over there, and something like that. For my blue one over here, I would see that I'm going to go and have a negative x. So I'm going to have a negative number, and then I'm going to have a positive y. So a positive number in the y, if I were to take a look at this vector over here. And then for this last vector over here, the red one, I would see that I'm going to, once again, here's my origin, so I'm coming back away. I'd have to have a negative x value, negative number, and I would have to have a negative y number like that. And I would have to go through each one of these, develop them as angles, so I'm going to have to take this one here, I'm going to have to go 180 minus 120, which is going to tell me that that one's going to be a 60-degree angle, and then I have to go and convert everything. Same with this one over here. This one's at a negative 120, so I can go and say it's at 180 plus another 60, which is going to take me to a value of 240, or I can go and say that this thing is going to be at a 60-degree angle on the inside. We always need to make it into these little acute triangles. All in all, I'm thoroughly unimpressed with the amount of work that this looks like it's going to go and be. And if I go through my module, I see pages and pages of big brain material where people have gone through and done just fantastic, but seemingly pointless amounts of converting stuff into x's and y's. We need to know that we can convert stuff into x's and y's. You know, that's the whole point of what we were covering over here, that we can split something up into these numbers based upon what we have inside of here, and we can add them together. We did that for this one over here, but there is a much simpler and easier method to go and do that, and that's going to be on your calculator. Let's take a look at that. Here's your calculator. Now, up in the top side over here, they show the screen. If your calculator is inside of what we refer to as normal mode, you're just going to go and see this up top here. That's going to be degrees. I'm going to teach you. This is so critical, you know, to covering stuff this year, because we're going to shortcut from this point forward. I'm going to teach you how to go and use the complex mode inside of your calculator, which is going to shave time off of your calculations over here. What we're going to do is we're first going to change our mode. Up top over here, you should have a mode button. When you press mode, it gives you a bunch of different options, and you can hit enter wherever you see that little period. That's the mode that you're in. So if I cam over, I see that now the periods over here. Identify them in stat, equation, or complex. I want to go to complex. Alternatively, if I go back here, I can go mode and just hit the number 3, which puts me into complex. I'll just clear that, put myself back into mode 0 over here, and I'll do it the longhand way. The longhand way is mode, over, and then hit enter. See how there's a little enter down there, which will put me into complex. Since you go into complex, what you should see is a little XY up top. That's a fantastic sign. It means that we can do something with X's and Y's. At this point, we would be in what we refer to as rectangular mode inside of here. We've got another mode that is going to be my polar mode. Polar mode is found right here above your number 8. Your number 8 has got a arrow R theta. If I go second function and then 8, what it's going to do is it's going to change me into a polar format. You need to be in polar format for a lot of the calculations that we're going to do. You can convert back and forth from polar to rectangular as well. Let's go right to the very top of this learning task over here, and let's just take a look at a simple 3, 4, 5 triangle. Okay, we've talked about the 3, 4, 5 triangle before. 5 as being my x value, 3 as being my y value, 5 as being my hypotenuse, 4 is my x, 3 is my y, like that. We've gone through this triangle before a couple of times. We know that this is roughly 37 degrees. It's actually 36.9 degrees. But what we can do is we can use our calculator to go and show all of these different angles. So what we're going to do is, first of all, we're going to go and find this angle over here using just my values of x and my values of y. Do you remember at the very beginning of this module where it said, hey, or this learning task where I said, what is the angle this is at? This is at an angle of 0. This one over here, because it's going up, is going to be at an angle of 90. Okay, we're going to go and use those with this calculator to go and put ourselves into the proper one. So we're in polar over here. What I want to do right now is I'm going to go 4. That's my magnitude, right, that we have over here. Now I'm going to go and find my angle. Angle is right below this DMS that we have over there. You should see a little tiny angle underneath there. I tap that, puts it in. If I'm in polar mode, it'll put the angle in. So it says 4 angle 0. That's what we have over here. Plus, right, we're just adding these things together, tip to tail. So 4 at angle 0 plus 3 at angle 90. 3 angle 90 equals, would you look at that? We get out a value of 5. So this tells me that I'm going to go and have a magnitude of 5. Let's just put that in here. So far, no big surprises. That's what we expected to see. It tells me I got a magnitude of 5, but then what it also does for us is it tells us the angle. And to find the angle, what we have to do is we have to use our comma, which is right above the EXP. So we go second EXP. And it shows a little tiny angle over there and tells me that I'm at 36.89 or 869899765. It's giving it to me really, really accurately over here. It tells you your angle. And I can go from there, I can comma back. So magnitude, angle, magnitude, angle, like that. It's fantastic. It tells me exactly what my angular degrees are. Let's go back into these ones. Remember how I said let's go and put them in at angles? We can do the exact same thing off of here. I mean, that one we're pretty confident what we're going to get. 12 angle 0 plus 12. Oh, that's one too many. Delete. Angle 0 equals 24. And if I go to this, it doesn't show me any angle because if they're all at angle 0, it just doesn't show anything up there. It just kind of looks at me and says, hey, you should know this. But it gives me that value, 24, right? That makes sense. What we had for our resultant over here. Let's try this one. 12 at angle 0 plus 6 at angle 180 degrees. 12 angle 0 plus 6 angle 180 equals a value of 6. Once again, when I try to find an angle, it doesn't show me any angle because it's still going to be on that 0, but it fits. It gives me the correct resultant vector that I'm going to have out of that. So far, not mind-blowing. This one over here, we can definitely do this one over here. If we once again identify them at angles, 80 at angle 0, 60 at angle 90, like that. 80 angle 0 plus 60 angle 90 equals a value of 100 at an angle of 36.86. Does that line up with what we have over here? Absolutely. 100 at an angle of 36.86 or 37 degrees. It's our 3, 4, 5 triangle that we have. So far, everything is working out. Let's take a look at this one. This one we calculated as being 13.3 at an angle of 11.6, but we did a little bit of rounding as we got there. If I want to be truly accurate, I'm just going to go and take each of these individual values and add them straight in. 6 at 90, 8 at 0, 10 at 300. Let's go and do that. Which was the first one? 8 at 0 and then 6 at 90. 8 angle 0 plus 6 angle 90. It doesn't matter which order they go in. I'm just adding them so it lines up with what we have inside of the book. Plus 10 at angle 300. 10 angle 300 equals 13.269. It is more accurate than what we calculated. Cross that out. 13.269 at an angle of, second function, comma, negative 11.56. Note how it says negative. See that negative over there? That tells me that it's pulling this thing down from my origin in that same direction. This is fantastic. You guys have no idea how much time this is going to save you if you can actually handle this thing inside a polar like this. Do you want to see something else that's even more fantastic? Like this, we saw that we could go and take all of these values over here. We could add them all up till we got to this 13.269 at a negative 11.56 degrees. What we can do is we can actually develop these x and y values from this. Watch this. If I now go and do a conversion, see how we're in polar? We can convert this to rectangular mode. I'm just going to go to above my 9 here, xy. As soon as I go convert to xy, it takes that same polar format. It's now converting it to an x value. That's the first thing. And then I go second comma. My y value is negative 2.66. That identifies it with an I or a j operator that we are going to go and have on here. So negative 2.66 as my y, 13 as my x. 100%. That lines up with what we see off of this triangle over here. This triangle is the results of us adding these ones all together. So it allows us to jump around. You know, a lot of steps that we would have to otherwise do through our longhand trigonometry, we now just kind of jump to the correct answers really, really quickly inside of here. Conversions are really easy. Adding is really easy. We can find the differences or voltages between points really easily as well. Let's go back to this one. Do you remember this one? This is the one that I didn't want to calculate, and I didn't want to calculate it on a video because doing all of those x's and y's is a little bit pointless. We've gone through the theory. We've understood that, you know, all these x's and y's, how they have to operate, how they tie together. I will ask some questions in this exam that we'll have to do with you being able to do actual trigonometric functions inside of these. And I'll ask for some longhand, you know, examples as well. However, most of the work that we're going to do this year, we are going to punch in inside of polar format, and then we're going to convert it back into rectangular if we need x and y values. Let's take this one. We're going to go and add this whole thing together, and we're going to find our result. Now, I'm just going to do this thing roughly the way it would look. If I were to add tip to tail, this one would come along there. Then I would see that number 2 would come up like that, and number 3 would come down like that. So I'm knowing, or I'm guessing, that I should be ending somewhere right up over there. Theoretically, you know, that's, or not theoretically, but just rough guessing and looking at the way these things add together physically, we can make this assumption that's where we would be able to end up at. Let's go and add them together. I'm just going to move them over to the side over here. Number 1 was 150 at angle 0. Number 2 was 100 at angle 120. And number 3 was going to be 70 at angle 120 as well. I'll add all these together, so I'm just going to clear. Note that I'm in XY right now. I can add polar even though I am in XY format. I'm just going to identify it as polar, so I'm just going to do 150 angle 0 plus 100 angle 120 plus 70 angle. This one over here, sorry, I wrote that as 120. It should be negative 120 that I have over there. So I'm going to make sure that I put that in there. Negative 120. You can actually add it in as being, positive 240 or negative 120. It'll treat it the same way, either way, equals. And now spits out a number of 65. Now, wait a minute. Where's the 65 coming from? Well, the 65 is coming from the fact that we are in X and Y still. We haven't converted. So what this is actually spitting out for me is that it's spitting out that I'm going to go and have an X value of 65 that I'm ending up at. That's about where we figured it would be. So an X of 65. And if I want, I can go and find my Y value of positive, that's what that sign is over there, positive approximately 25.98. So I'll just put that up there, 26, roughly, that we are going to go and have. Alternatively, I can go and change that thing into just my full polar. Let's just go do a conversion to a polar format. We have an XY number, polar format. Tells me that it's going to go and be in total overall, that is going to be 70 at an angle of 21.78. This line over here, 70, 21.78 degrees that I'm going to go and have. If you take a look in your binders, you go through all of theirs, you go all the way through, you should find that you are going to go and have at the very end of that calculation that they do the really, really long way, they show you 70 amps at an angle of 22 degrees. We did the same thing. We just jumped around to it. We got right over to our X, Y, and our polar values just by adding them together. This is going to be incredibly handy later on where we're starting to go and add stuff inside of our calculator. One more thing that we're able to go and do with these. Let's just go back to this one over here. Do you remember how we added these two together? We said that we're going to do 80 at an angle of 0 and 60 at an angle of 90, and it gave us, the proper value, 100 at 36.78. If I have something that is truly X's and Y's, or J's, J operators, off of here, I can input them directly as X's or Y's. And I can do that, once again, I'm going to make sure that I'm still inside of either polar or rectangular. It wouldn't matter which one, but I'll go polar. I could go and input them directly in. So I'm going to put this in as my X value, 80, this as my Y value, and I just need to identify it as a Y value. So I'm going to go 80, it knows it's an X, plus, and then I'm going to go I60. That's going to identify this I over here, and it's right there on the ABC. That identifies it as being a Y, and I hit enter, and it tells me that I've got a value of 100 at an angle of 36.87. So if you've got 90 degree apart components, you can just go and add them directly together. You don't have to put them in as, 80 angle 0 plus 60 angle 90. You can. You'll get to the same result either way, but it's just one more method that you can use this fantastic little sharp calculator that you're given on every exam from this point forward, but you can use it to go and cut out a lot of the work that you have in front of you. All right, that is it for this one over here. We are now through all of our base trig. We're going to talk a little bit next about some AC problems, and then after that, we're going to get into the heart of what we need to cover for our theory.